Hello, everyone. Welcome to my talk. My name is Xiaoting Ouyang, and I'm very happy to talk about our recent results of consistent query answering for primary keys on past queries. The past queries we consider now could contain self-joins. This is a joint work with my PhD advisor, Paris Couturier from University of Wisconsin-Madison, and Jeff Wyson from University of Mons. So let's get started. In our work, we consider primary key constraint as the only integrity constraint, and we want to study the inconsistent database that could possibly violate a primary key constraint. And that means each primary key could correspond to multiple facts in the database. And when we have such an inconsistent database, what we want to do is to repair it. And the repair, we mean to select a maximal set of facts in a database that still satisfy the primary key constraint. As an example, you see that this database is actually inconsistent because the key UW corresponds to two facts in the university table, one in Madison and the other is in Seattle. And to repair this database is actually to decide which one do you keep among these two facts. So you see each inconsistent database might have different repairs, and actually different repairs might give different answers to the same query. So for example, if the query is there university snowing today? If the fact you keep is UW in Madison, then you would answer yes, because Madison is snowing. But if you keep UW in Seattle, you would answer no, because Seattle is not snowing. So what do we do about this? We consider the problem of consistent query answering for some fixed Boolean query Q, which we denote as certainty Q. The input to this problem is an inconsistent database, possibly violating the primary key constraint. And the question we want to ask is this fixed Boolean query Q evaluated to be true in all possible repairs? And this is interesting because if we could answer yes to this problem, that means no matter how you repair the database, the answer will still be yes. So in some sense, there's no need for you to repair it. As you formulate this problem, you will realize that this problem is always in co-MP because you could always go through all possible repairs to check whether this query Q is true or not. And we do know that for some queries, say for example, Q1, this certainty Q1 problem is in FO, meaning first order rewritable. And that means to solve this problem, all you need to do is to evaluate some first order formula. And this is really powerful because evaluating one single first order formula simulates going over all possible repairs, which could be exponential. So this is really efficient. However, we do know that for some queries, say for example, Q2, this problem is co-MP complete. So the question is, for which queries is this easy to solve, and for which one it is very hard to solve? And this is naturally a classification problem, and it has been long conjectured that this problem is either in polynomial time or co-MP complete. And there's a long line of research trying to show this conjecture, as early as 2005, when Foxman and Miller looked at a very specific type of Boolean conjunctive query, all the way until 2019, when Couturier and Wyson shows that for any self-join-free Boolean conjunctive query, it is either in FO, L-complete, or co-MP complete. And in particular, they show that for any self-join-free pass query of this particular form, it is always in FO. And for pass query, it is all binary atoms, which can think of as a pass going from x1, x2, x2, x3, all the way to xn plus 1. And all the relation names are distinct. And we can use a word to denote this kind of pass query. And as you can see, all such results consider self-join-free queries. And our contribution is that we remove the self-join-free constraint from the pass query and show that this problem can be in FO, NL complete, P complete, or co-MP complete. As an example, you see that here, this pass query, RRX, there's a self-join between the first two atoms. And this is really interesting result because we see some very new complexity classes like NL complete and P complete that don't exist for self-join-free cases. And also notice that for this kind of pretty simple structured query, the complexity is already very diverse. And I do want to mention that self-join has already been a known obstacle for many problems in database theory. So multiple dichotomy results exist for, for conjunctive queries without self-joins. And last year in pods, for query resilience, the authors show a nice dichotomy between P time and NP completeness. And they consider a very specific type of self-join. And our work try to provide some insights on how to handle self-joins in a more general sense. In the remainder of the talk, I will talk about how we handle the self-join, present our classification results, and finally give some proof sketches. So first, how do we handle the self-joins? We use this notion of rewinding. And first, let me set up this problem a little bit. So we still consider the problem of pass query RRX, and the input to this is an inconsistent database, which we could represent by a directed graph where each edge corresponds to one fact and the color is the relation name. And the question become a graph problem. The question really is, do all the repair really contain a pass colored of RRX? So we look at the first repair, you see that there's a RRX pass as highlighted. And this RRX pass could really be satisfied, starting from 0, you have seen the first R, second R, and the last X. So this is good. And you can see that in the second repair where you keep the other R12 fact, there's also a RRX pass, but this time this pass starts from 1. In our setting, we really want all the paths to start from the same constant. So we really want to start from 0. So how do we start from 0 in this case? Well, we start from 0, we grab the first R, and then we grab the second R. And here's the notion of rewinding. Because there's a self-join in a query, we could always pretend that the second R that we just saw was actually the first R. And we rewind back to the stage where we pretend that we just got the first R, and then we continue onward to satisfy the query. As you can see, you can do this rewinding over and over, and doing this essentially results in a regular expression of this form. And we were able to show that we can answer yes to certainty Rx problem if and only if there's some constant C. And in our example, this 0, in all repairs, there's a pass whose color is of this particular form. So as you can see in this crazy example, there's a notion of reachability, and you can get a sense of why this problem could ever be NL complete. And now the question is, how can we find such a regular expression of this form? Naturally, we turn to the NFA, and recall that this is really the process of satisfying one pass query. And all we need to do is to allow one to jump back to a previous stage, and we could do that by allowing some epsilon transitions between the stages. And we associate each of these NFA to each pass query. And also you can see this very crazy example, although this might look very complicated, but the point is this NFA will be of constant size if the pass query is considered a constant size. So why do we need this NFA? Because we need this for our classification results. And here is how we classify consistent query answering for pass queries. So the first condition says that if the pass query Q, when you think of it as a word, is a prefix of every word in its NFA, say for example, RX, then we would say that, okay, certainty Q1 must be in FO, or otherwise we conclude that it's in NL hard. As an example, RXRY, because RXRY is not a prefix of this particular word in its NFA, RXRXRY. And you see that although this is not a prefix, but still it is a factor. And there's a very similar condition that says that this query Q is a factor of every word in the NFA, then we will conclude that this problem is actually in P polynomial time. Or otherwise, we will say that it's in co-NP complete. And as you can see in this example, RXRX, RYRY is not a factor of this particular word in its NFA, so certainty Q4 is co-NP complete, but certainty Q2 is in P time. And we were able to find one very tricky condition to separate the P time and NL hard cases to make them complete. And this gives the full classification result. And also, all the conditions that I just mentioned are decidable in the size of the query, and therefore, given any pass query Q, we were able to decide whether it is in FO, NL complete, P complete, or co-NP complete. And finally, some proof sketches. And first, this is really the key lemma behind our algorithms, we were able, this is a very similar version to the one you just saw. So we were able to answer yes to the certainty Q problem, if and only if we were able to find such a constant C, such that in all repairs, there's a path whose color is in general accepted by the NFA that I just introduced. And moreover, the second condition can be decided in polynomial time using either dynamic programming or least fixed point logic. So some intuitions on why this might hold. So condition, recall that C3 says that Q is a factor of every word. And item 2 says there's a constant C such that in all repairs, there's a path accepted by the NFA. And because Q is a factor of every word, so you would be able to find Q somewhere in between, and therefore all repair will contain Q. So this shows one direction, and the other direction for the proof, please check out our paper. For the FO case, because Q, now we consider C1, where Q is a prefix of every word. So essentially, there's really no need for you to come back. And therefore, all you need to do is to check for a path of exactly Q in all repairs. And because the size of Q is a constant, so you will be able to check item 2 using a fixed size first order formula, and that is in FO. And finally, the hardness results. I do want to mention that for p-time hardness, we had a reduction from monotone circuit value problem, which essentially says that, to evaluate the circuit containing only AND gates and OR gates, we were able to encode this problem using consistent query answering, which is kind of interesting. And finally, some future works. For this work, we only consider path queries, so we definitely want to extend to other more general queries like acyclic queries, maybe more arities, maybe even graph queries. And finally, we will want to extend to more general, integrity constraint like multiple key constraint, maybe in negated atoms, or sometimes with aggregation. And that concludes my talk. Thank you so much. And I'll be open for any question you might have.